Okay, the title of this is number 1, Planet Earth. And this corresponds to the first chapter in the textbook and the first section in the specification. Now, this really involves quite straightforward stuff today. We've got the structure of the Earth. We've got a little bit about latitude and longitude, and I guess that's the most astronomical of all this. Latitude and longitude is really related, coordinates on the Earth to coordinates in the sky, and that is really the feature of, I think, next month's session, and that really is quite complex. We're going to have to whiz through next week. Hopefully we'll cover everything. And then just a little bit about the astronomical significance of the Earth's atmosphere. So 3 sections. Again, what I'm doing for simplicity and to make it clear to you all is going through more or less in the order in which things are in the book. Okay, I think we're all here. I think we've got about 12 students, and when you are starting to enter, it's coming up on my PowerPoint screen, so all is fine. Presumably, all you can see is what's on my PowerPoint screen. So we'll deal with the Earth structure first of all. And right, here we are, here we go.
We can only see you. Sorry, Nigel, we can only see you.
Oh, you can only see me? Oh, no.
Yeah.
Sorry. Yeah, we can only see you. Sorry, I'm just trying to texture that, Nigel, so we can't see your PowerPoint yet.
Thank you very much. Right, okay. So I need to go into Zoom again. And I need to share screen. Right.
That's it.
And I need to share screen with PowerPoint.
That's it.
Thank you very much, everybody.
Phew. Thank you, Elaine.
Now let's see if this works. Share. And presumably, let's just go back to the beginning. Then we're from the beginning. Right.
Excellent stuff. Yep. Okay.
We've got webinar 1, Planet Earth. And Aidan is just joining us as well, and we don't want that, and we do want the PowerPoint. Right, so we got the Earth structure and a few facts and figures. Okay, I don't need to read these really, but these are sort of random facts that you need to know about the structure of the Earth. The Earth is very nice as a typical planet because it's, well, the largest of the terrestrial planets, but the interesting planet Venus is about the same size. So we've got the mean diameter of the Earth there. I think you've got to be careful with that if you're asked questions about, say, the height of satellite orbits and the orbit radius and things like that. So do be aware that you might have to change the diameter of the Earth into a radius, which of course is 6,500 kilometers. So we know that it's a kind of sphere. It's actually the least spherical, I think, of the Sun, the Moon, and the Earth. The Sun is the most spherical, which quite surprises me, actually, being so big and moving so quickly around the equator. So its official description for the Earth's shape is an oblate spheroid. There we go. So it's slightly squashed at the poles by something like 40 kilometers or thereabouts. So imagine a child sitting on one of these big bouncy balls and sort of squashing it at the poles. More about the poles later on. We've got 4 internal layers. There's a nice diagram on page 3 on the first page of the textbook looking at this. Those will come up in a minute. And then we've got the oceans of water and the seas and the atmosphere above. And in fact, depending on which geography book you read, typically 70 to 75% of the surface is covered in water. Now that's quite worrying, actually. You might ask, why is Nigel worried about that covering of water? And it's because if, or rather when, we are struck by a significantly sized meteoroid or even asteroid, it's most likely to end up in one of the oceans, and that will splatter lots of water into the atmosphere, and then it's anyone's guess what might happen. Probably the temperature of the Earth will rise fairly significantly. It's not going to be too good if a big rock hits land, but really serious if it goes in the oceans, because then water vapor, a great amount of water vapor, will be present. Now, as we go down, perhaps it's sensible to look at the structure now. Let me just go back to the diagram. Right, as we go down from this, and as I said earlier, some of you who've joined more recently didn't quite hear this, I'm using diagrams from the book, so really you won't need to sort of sketch them as we're going on, so you can make little notes about other things, or just simply sit back and listen. But we've got the main regions of the Earth here on the right-hand side. The crust, the rocks on which we stand, mostly silicon dioxide and calcium carbonate, depending on whether we're talking about igneous or sedimentary rocks. Underneath, we've got the mantle, which is a kind of very viscous, very treacly, gooey sort of mix, really, of rocks and what's fairly underneath. The cores, the outer core and the inner core, you'll notice are quite significant. And the outer core is particularly interesting because it's a liquid. Now, we know all this because we have sent shock waves through the Earth. Some of them occur naturally when we have earthquakes, and some are created artificially. And if we trace back the path taken by these seismic waves, as they're called, geologists and other scientists can actually work out what the internal structure of the Earth is. So don't be thinking we've ever been down to such distances or anything like that. That would be very unwise, because the temperature increases as we go down and the density increases as we go down. And it's interesting to think that the crust, you know, these rocks that we sort of pick up on our travels that might be quite heavy, the crust is actually floating on the mantle. And in fact, the crust is actually split up into a whole number of, I suppose I could call them big rafts that sort of move sideways and collide with each other. And this is the whole science of plate tectonics. Well, luckily, that doesn't come in astronomy. I think you'll agree there's enough in GCSE Astronomy as it is, without any more. But the outer core is very interesting, because in the outer core, it's a liquid. And charged particles, we'll hear a lot about these. So these are nuclei of atoms and free electrons flowing in rather uncontrolled paths. Now, those of you at school, if you're anything like year 11 or above, and those of you who, like me, were at school a few years ago, will realize that when you have an electric current flowing, it gives rise to a magnetic field. It has a magnetic effect associated with it. So basically, the outer core, all those charged particles that effectively is electric currents, flowing in rather undefined loops, gives rise, on the whole, to the Earth's magnetic field. And that is very important to us because it protects us. It acts as a kind of shield by deflecting charged particles from the sun that we call the solar wind. Now, that's going to feature more in next week's webinar for those of you who've signed up for both year 1 and year 2 webinars. So that's the first topic that we would do in the second year. So that's coming up next week, the solar wind. For now, the outer core is the source of the Earth's magnetic field that does wander, it does move. At the moment, it's very close to the geographic pole. We'll get onto that in just a minute or two. Right, and then we have water on the surface, as we've been talking about, and an atmosphere of nitrogen and oxygen, sort of 80% nitrogen, 20% oxygen, just to sort of one significant figure. We're not interested in detail of that. One or two other gases as well. Argon is the next one. We've got a bit of water vapor, an insignificant amount of carbon dioxide, but that's getting larger. There we go. That's the structure of the Earth and the internal structure. Just as a kind of basis for other planets and the moon. So later on, we'll see how the moon compares with its relatively small core It's interesting, actually. I must just elaborate a little bit before we get on to latitude and longitude, because the time actually is going okay. Mars doesn't have an atmosphere, and the Earth does. Now, this is believed by many to be due to the fact that Mars is smaller than the Earth, and therefore not as hot, and internally not as hot, and so it doesn't have an outer core. So electric currents don't flow through the outer core of Mars because it's solid. And therefore, Mars doesn't have a magnetic field, and therefore the charged particles from the sun in the solar wind can interact with the particles in what might have been once Mars's atmosphere and blow them away. So there's a simple explanation of why the Earth does have a magnetic field that deflects charged particles from the sun, and Mars doesn't. Mars wasn't hot enough to have a molten interior. By the way, the core of the Earth is mostly two elements, nickel and cobalt. Oh, and iron, sorry. Mostly iron and nickel, let's just correct that. Mostly iron and nickel. Now, we associate these with magnetic materials. And in fact, these may well give rise to some of the magnetism, but the main source of the Earth's magnetic field is the electric currents flowing in the outer core. Right, good. The inner core, by the way, the pressure there, due to all the weight of the rest of the Earth, is too high for a liquid to exist. So the inner core is a solid. All right, let's move on then to part 2, latitude and longitude. Now, you're probably familiar with these on a map and are probably more used to thinking that lines of latitude and longitude are actual lines, but they're not, they're angles. Just like you're taking a little bit of the map there, the lines of latitude are the ones that are running sideways, and the ones of longitude are the ones that are running north-south. Now, these aren't the actual, the numbers on here aren't the actual latitude and longitude. They're just numbers on this Ordnance Survey map. But if they were, the nice one going through 0, 0 towards the top left would actually end up, once it's left some part of Scotland, I think, what it would do is end up passing through Greenwich in London. So we are going to stop thinking about latitude and longitude as lines on a map for now. We're going to consider them as angles. And all these angles, as you'll see from the diagram in a moment or two, are from the center of the Earth. So we've got to do a lot of imagining, certainly in the whole course. But for today, we've got to imagine that we're standing at the center of the Earth with our arm sort of pointed outwards horizontally. Okay? And we're going to move our arm either upwards or downwards. And we're going to move our arm eastwards or westwards. And then our arm will intersect different lines of latitude and longitude. Here we are. So we've got this diagram again from the book. And let's deal with longitude first of all. So we've got our North Pole at the top of the Earth and our South Pole at the bottom. And we've got a line of longitude that goes from the North Pole down to the left a little bit, vertically downwards, through a little dot, back to the dot at the South Pole, and that is the Greenwich meridian. That is defined by international agreement as 0 degrees longitude. It's not east or west, it's 0 degrees. It's like midnight, it's not 12.00 AM or PM, it's 12.00. I think I make that point in my book. Really bugs me when I see signs saying open at 12 PM. What does that mean? Not a clue. Anyway, let's imagine that we are at the blob on the right-hand side on the equator. Talk about the equator in a minute. If you imagine that you're at the center of the Earth and you point your finger towards the Greenwich meridian, so along the dashed line on the left of the 85 degrees, and then you swivel round to 85 degrees to that blob on the surface of the Earth that doesn't have a label, you've swung round through 85 degrees and you've gone eastwards. So the longitude of that point will be 85 degrees east. All right, now let's go back to the center of the Earth and let's find the latitude of the point that has a longitude of 85 degrees east. Well, again, we point at the equator horizontally and then we go upwards. So to find longitude and latitude, we're at the center of the Earth. We point towards the Greenwich meridian and then go left or right. When we're doing latitude, we point at the equator and we go up or down. So the longitude and latitude of that point that is labeled, the longitude is 85 degrees east. So we've gone round 85 degrees eastwards from the Greenwich meridian. And we've gone upwards from the equator that's defined as 0 latitude. We've gone up 78 degrees in the north direction. So one important thing to remember, unlike with stellar coordinates, we have north, south, east and west. Unless we're talking about the North Pole or the equator or the South Pole. And then we just need a number. Okay, the North Pole doesn't have a longitude because all the lines of longitude actually converge there. So the equator is just 0 degrees. The Greenwich or prime meridian is just 0 degrees. The longitude of the North and South Pole are 0 degrees. But everything else has either north, south, east or west. All right, everybody. If you're jotting down questions, I can't see them at the moment until the end, but I think that probably we're reasonably happy about this. Now, in astronomy, let's remember this is GCSE Astronomy that we're studying, the most demanding GCSE by far. I was giving a talk to Macclesfield Astronomical Society about 18 months ago, and I was just presenting just for 20 minutes the new GCSE specification. And we had one of the lecturers from the University of Manchester there who I know who operates the Joggle Bank telescope. And he said, Nigel, this is first year degree stuff, most of this. First year degree stuff. And as you've probably seen from some of the questions, if you looked at the assessment questions published by Edexcel, some of them are quite demanding. But hopefully, and I'm confident, we're going to rise to the challenge. So, you know, you're in good hands with Alistair and I and your tutors, and you know, do make use of them. So we've got some special latitudes. We've got the equator at 0 degrees, just talked about that. And we've got the geographical poles. Now, at the moment, we're forgetting about the magnetic poles. They are irrelevant to this study of latitude and longitude. So the poles geographically, 90 degrees north at the North Pole, 90 degrees south. Now, interesting lines of latitude are the tropics. Now, we have 2 tropics, and they're at 23.5 degrees north and south of the equator. 23.5 degrees is going to be an important number. All right, it doesn't matter if you write it as a decimal half or a 1/2. That doesn't matter at all. 23.5 degrees north is the Tropic of Cancer, and 23.5 degrees south is the Tropic of Capricorn. And perhaps less significant is the Arctic Circle at 66.5 degrees north and the Antarctic Circle. Now, the interesting thing is 23.5 and 66.5, if you add them up, make 90 degrees, make a right angle, and that's going to be quite significant. Right, well, this 66.5 degrees or 23.5 degrees is all to do with the tilt of the Earth's axis. So let me just explain a little here. I'm sure we've seen a diagram like this in primary school, but perhaps we didn't understand all the significance. Now, the Earth orbits the Sun in 1 year, we know that. but the angle at which it rotates is actually tilted. Now, a lot of books get this wrong, and the media get this wrong as well. The tilt is actually at 66.5 degrees to the plane of the Earth's orbit. The plane of the Earth's orbit is just the kind of imaginary flat surface along which the Earth is embedded and going round. A lot of people say the axis, no, it's tilted at 23.5 degrees. But that's to an imaginary line that, if you look at the diagram here, is sort of vertical. So it doesn't matter whether you talk about the tilt of the Earth's axis at 23.5 degrees to an imaginary vertical line, or whether you talk about the angle is 66.5 degrees to the plane of its orbit, what we call the ecliptic. Don't think that features in here, that will come in later on. But the plane of the Earth's orbit around the sun is called the ecliptic. It's also a line on the sky, but we'll talk about that in a couple of months' time. So the reason we have the Tropic of Capricorn and the Tropic of Cancer and the Arctic and Antarctic circles where they are is because of the tilt of the Earth's axis. And more or less all the planets are tilted in relation to their orbit. It's good evidence to support the idea that early in the solar system there were a lot of collisions. There were a lot of bodies and a lot of collisions. And collisions can quite easily cause the axes of planets to change. Look at Saturn. Look at Venus. It's almost flipped over. Venus spins not from west to east like the rest of the planets, but from east to west. It's almost been turned on its head, which is quite amazing. However, let's get back to the job in hand. Latitude and longitude. Whoops, I didn't mean to do that. Right, now, what are these latitude and longitude then? Well, if the Earth's axis is tilted, let's say at 23.5 degrees to the vertical, the Tropic of Cancer marks the most northerly point of the Earth with respect to the Sun. The Earth's axis is tilted towards the Sun. Just going back to the previous one, we're in the right-hand diagram at what we call the summer solstice. So on June or thereabouts the 21st, the summer solstice occurs. And that's when the Earth's tilt, because it keeps that same axis of tilt, but it moves around the Sun. The Earth is tilted towards the Sun to its maximum extent. That's in the northern hemisphere. So if you're on the Tropic of Cancer, on June the 21st, you will see the Sun rise due east. At noon, it will be directly above you, and it will set due west. And that's quite significant. The furthest north that the Sun sort of reaches. So again, if you were on the Sun looking downwards, directly below you would be this imaginary, well, you'd see it as a line, of course, Tropic of Cancer. 3 months later, and we're in the autumn, coming up to it fairly soon. The autumnal equinox. On September 23rd, give or take a day or two, the Sun is above the equator. You can see the tilt of the Earth's axis on the diagram there is neither tilted towards the Sun, like it is at the summer solstice, or tilted away from the Sun, as it is in the winter solstice. Again, I'm talking about the northern hemisphere. Oh, I've just noticed that I can use my cursor. There it is. That might be quite useful. Sorry, I'm still a novice with Zoom and the way this presentation is happening. So basically, what we are saying is that, here we are, a nice little table here. So the significance of these special latitudes is all to do with the Sun. And the Sun, let's face it, gives us our weather, our nice sunny, warm, hot weather in Britain in the summer, and vice versa in Australia and South Africa and so on in our winter. So what you've got to be aware of is these dates, the names of the events, and where the Sun is. and to kind of explain the relationship between them. So I've put this table here. This might be useful to just jot out. So I'll just be quiet for half a minute. I think if you use some abbreviations as well, I think then you can maybe write this a bit more neatly and comprehensively later. Notice September's the odd one out. This is all to do with how many days there are in months and so on. So no wonder meteorologists actually use March the 1st, June the 1st, September the 1st and December the 1st to mark the start of spring, summer, autumn and winter. Astronomers use these dates, which are of course related to astronomical events. So September is the only one. I think if you wrote it in an exam, if you were asked about this as September the 21st, I think you would probably get away with it, even though it's not strictly correct. Right, good. Let us move on. I can always put this table back up later on. So the tropics are going to mark the maximum angle from the equator in a north and south direction from which the sun can be seen to rise. Now, I think what I meant to do here was to say that those are not the tropics, the circles, the Antarctic and Arctic circles. Now, I think I've had some problem cutting and pasting here. So what I'm going to do is just escape and just change this. Hopefully you can see this, and then go back to the slideshow. Right. Sorry about that. This is the first run through, everybody, and I did run through and talk to myself about it, because I must have missed that little bit. So the Arctic and Antarctic circles, these are the tricky ones. These mark the most northern latitude and southern one from which we can see the sun rise and set every day of the year. If you're on the Arctic Circle on December the 21st, because the difference in latitude is 90 degrees, the sun will actually be seen to go around in a kind of circle or a kind of half circle. It might half rise and be half risen and half not risen. It'll sort of go around in a circle on your horizon. Any further north and you won't see the sun for a few days or weeks. Okay. Similarly, if you say are on the Arctic Circle on June the 21st, then you're likely to see the sun all night long, the land of the midnight sun and all that sort of thing. That needs a little bit of thinking about, and thinking about where you are and realizing that you've got a horizon and that you can't see below the horizon. All right, we may come back to that in a little while. So apologies for my calling those the tropics. Those are the Arctic and Antarctic circles. There we are, another viewpoint here. Now, this diagram is actually split up into two. The left-hand side shows what's happening in the summer to rays of light from the sun, and that's the left-hand side. The right-hand side shows us what's happening in the winter. So looking on the left-hand side, you can see that the big arrow is actually striking the Earth on the Tropic of Cancer. Okay, the big arrow is on the left and the Tropic of Cancer is on the right, but that's the line of latitude of 23.5 degrees north. The sun's rays in winter, rays of light from the sun, are focused on or concentrated on the point which, if we look on the bottom left-hand side, is the Tropic of Capricorn. Right, so there is the latitude, longitude We're going to use longitude very much with determination of time, and we're going to use latitude very much in conjunction with a star has these coordinates. Are you going to be able to see it all night long if you have 24 hours of darkness, or is it going to rise and set? Is it going to be at some stage directly above where you're observing from? So there's quite a lot to relate this. This is a kind of introducing the tools that we'll use later on, the latitude and longitude. As I say, longitude with time, or rather using time to determine longitude, and latitude looking at sort of whether or not stars are close to the pole star or further away from the pole star that makes them set, and so on. So relating all this to the stars, to real astronomy, certainly next month is going to feature quite a lot. Okay, well, we look at the Earth's atmosphere really from an astronomical point of view. I suppose in a way we wouldn't have any astronomers if we didn't have oxygen to breathe. So there's an obvious benefit there, and that would be sensible as an answer if you're asked to, you know, list 3 benefits of the Earth's atmosphere. A lot of the harmful ultraviolet radiation, and certainly X-rays and gamma rays that come from the sun, is absorbed. Now, not all of it. I think you're probably aware that the Earth's atmosphere acts as a big filter. It stops a lot of radiation from the sun, a lot of what we call electromagnetic radiation from the sun to reach the Earth's surface. The sun emits mostly visible light, you know, red, orange, yellow, green, blue, violet, and so on, which all get through the atmosphere. You would almost think it's a fluke that the composition of the atmosphere allows to pass through those radiations emitted by the sun. But it's not quite like that, because the sun emits ultraviolet radiation, which is a shorter wavelength than violet and blue. And it also emits quite a lot of infrared, which is kind of has a warming effect on the skin. Now, both of these in extremes can be potentially dangerous. Ultraviolet light on the skin can give us sort of skin damage, and in the sort of ultimate can give us skin cancers and things like this, although a lot can be treated. Infrared radiation can cause sort of skin burns and so on if you're exposed to sunlight for some considerable time. But a lot of the more harmful ultraviolet and infrared radiation just gets filtered out, just doesn't reach sea level. And of course, the infrared radiation is responsible. Some of it can come in but not get out. So we think the infrared radiation is certainly responsible in part for the greenhouse effect that may contribute significantly to the global warming of the Earth. And ultraviolet radiation used to be absorbed by ozone in the ozone layer. Now, the ozone layer has been getting thinner over the last sort of 20 or 30 years because chemicals have destroyed the oxygen-3 molecules. But I'm pleased to report the ozone layer is repairing itself, and so more ultraviolet radiation should be absorbed as it tries to get through the atmosphere. Right, okay, let's continue. Now, the atmosphere as well, and the sea, regulate our temperature. The fact that we have an atmosphere and the fact that we have water on the surface as well means that the Earth doesn't get too hot and too cold. I think the mean temperature is 15 degrees Celsius, which in our latitudes in the UK is quite nice. You know, I think in the winter, if you were given the option of having every day at 15 degrees Celsius, I think some of us might take that up. 15 degrees Celsius in the summer is a little bit cold, but there we are. The mean is about 15. It can get extremely hot. Some parts of the Middle East and some parts of the United States get incredibly hot. We hear, you know, 40 degrees Celsius, 45 degrees Celsius, and some, in fact, are extremely cold. I went on a school trip in the autumn to Russia, and we had a day visit to the Kremlin, and I've never been so cold in my life, and it wasn't particularly for the Russians a cold day, but I can assure you it was unpleasant. What the atmosphere also does is protect us from large meteoroids. And the smaller ones as well. They burn up in the atmosphere, not completely necessarily. And in fact, the burning up in the atmosphere, as well as thinking, oh, we're being protected from big chunks of rock that are heading towards the Earth, they also give us we see meteors shooting stars. And especially when we see coloured ones. These are larger pieces of rock that have possibly split up, and the elements inside have got so hot they emit light, characteristic of which elements they are, rather like fireworks. Really nice to see bright meteors, sort of, you know, not too far above. Meteors themselves are only maybe 10-15 kilometers up, something along those lines. But the atmosphere has problems, has drawbacks for astronomers. The first one is that in the daytime, it's light. We have a blue sky, so we can't see the stars. And in fact, in the summer, even in the UK, it probably only gets dark for a couple of hours, you know, round about the summer solstice, June the 21st. The sun hardly gets below the horizon. So really, it's not a great time to observe stars in the summer. You will need to consider all this when you are planning your projects in the observational skills section of this. Remember, you have to carry out at least 2 full projects, one of which is planning. So it's no good to plan to observe seriously stars and constellations in the summer. What it also does, the Earth's atmosphere, it's moving all the time in lots and lots of different paths. It gets a different amount of energy from the sun. There are different conditions. The seas are warmer than the land, usually at night, and the whole atmosphere is turbulent, and this affects how light travels through it. So when light enters slightly less dense air, it changes direction. When it enters denser air, it changes direction again. And this causes light to come into our eye from slightly different directions. And that's why stars appear to twinkle or undergo what we call scintillation. So that's a problem of the atmosphere. Well, you might think, okay, I'm an astronomer, I'm an amateur astronomer, I like to go out and look at the stars. I think it's quite nice that the stars twinkle. Well, that's absolutely perfectly fine. You'll notice, though, that the planets don't, because light has come from a disk. I know it's come from a disk from the stars, but that disk is a long way away compared with from the planets. So really, although the planets, Venus and Jupiter, very bright at the moment, although light's coming from a disk, which doesn't have quite as serious an effect because the light changes direction on its way in. The stars are so far away, we consider them as points of light, as single points. All right, we talked about the others, absorbing X-rays and ultraviolet and so on, that can be quite dangerous for us, but some astronomers actually like to observe stars and galaxies and planetary disks around new stars in the infrared, ultraviolet for young hot stars, and X-ray regions. Astronomers can detect stellar black holes by looking at X-rays from stars. As the matter falls into the black hole and accelerates, it emits X-rays. So X-ray astronomers and ultraviolet astronomers have to do their observations either high up on mountains, that will do for infrared, but for ultraviolet and X-rays, they have to be above the atmosphere. So they have to be on satellites, and of course, they have to be high up. They have to be launched, they have to be built, so there's a whole escalation of cost. Another thing about the atmosphere is that it actually absorbs light. especially with stars near the horizon. So stars near the horizon aren't terribly bright. This is why astronomers tend to have this fascination of observing stars with telescopes or binoculars or the naked eye, it doesn't matter, as high as possible. So they get the most favorable chance, because if a star is as high as possible, then the light passes through the least amount of our atmosphere. So the best time to see stars in their best, at their best, is when a star is high in the south, crossing what we call our meridian. So if you go outside and look north and look south and then draw an imaginary line over your head, that meridian is an imaginary line on the sky. And when stars cross your meridian, when they culminate, we'll look at all these terms again later in the course, fairly soon in the course, that's the most favorable time. They have almost, astronomers, an obsession at observing stars at their best, so when they're highest in the sky. Good, so those are the drawbacks. Well, we're getting to one or two more now. The dreaded light pollution. Now, I split light pollution up into glow and glare. Sky glow and glare. Now, sky glow is this horrible orange, kind of fuzzy, rusty haze, which is close to the horizon. Now, some might argue, well, that doesn't matter really, because if you are looking at stars that are highest in the sky, the orange haze around the horizon doesn't really matter too much. But it just offends me that some people who do want to see stars close to the horizon, you know, catch the International Space Station at the moment it rises, we may not see it because its light blends into the background. So we've got this kind of background glow, certainly maybe 10 degrees, 15 degrees above our horizon. So the fainter stars are not visible because they just blend in. It's like trying to watch a movie with the lights on. It's just not the done thing, is it? Now, glare is the problematic light. This is usually white light. The orange haze is due to sodium lights that luckily being replaced on sort of motorways and on main trunk roads, but we still got a lot of them remaining. Glare is light that enters your eye and it affects your night vision. Let me just explain a little bit. When you're going out observing, your eyes don't get used to the dark. That's a phrase I used to use. They don't become dark adapted for about half an hour. Now, it's all to do with the cells in the back of the eye, the retina, that are sensitive to light. There are two lots of cells called cones and rods. Now, the cones are sensitive to bright light and they can detect colour. The rods are sensitive to dim light and they can't detect colour. That's why we can't see coloured things at night, unless they're emitting light, obviously. Now, it's the rods that we want to use to observe the stars. And in the in the daytime, they are too sensitive. They are oversensitized. So getting used to the dark adaptation means waiting for about half an hour for the rods to become far less sensitive. Sounds strange, but that's the way it is. Then we've got the colour receptor, we've got the black and white receptors of light and dark, and we can see the stars. We can compare magnitudes, we can compare brightnesses. We might be able to see the odd colour if we imagine that Betelgeuse is red, or Aldebaran is red, or that Deneb is blue, but really trying to see colours of stars, they do have colours, is a little bit difficult, because really there's not enough light to affect the cones. Once you've got the rods dark adapted, any amount of light falling onto them just ruins that dark adaptation. So if a car suddenly comes around the corner, it's headlights blazing in your eyes, or somebody switches on a security light, or somebody, your neighbour, if you're watching from the garden, switches on the kitchen light, that ruins your dark adaptation. So again, if you are planning from where to observe, bear in mind that you don't want any security lights, car headlights, street lights, or car park lights on, because these will seriously affect your ability to see faint objects. You have to keep waiting for another sort of 15-20 minutes, maybe not the full half hour, to get your eyes sensitive or desensitized again to be able to see the night sky. Well, ladies and gentlemen, boys and girls, students, astronomers, that is, in 45 minutes, which is what we planned, the presentation on planet Earth. We've looked at the internal structure as a kind of model for other planets. We've looked at latitude and longitude, that is going to feature a lot as we go through this. I mean, astronomy, modern astronomy was invented to be able to navigate, basically, wasn't it? I know I'm talking extremes here and being a little bit black and white. But yeah, astronomy really has arisen out of the need to navigate at sea. So we've looked at latitude and longitude in quite a bit of detail, and then we've studied the Earth's atmosphere just from an astronomical point of view, really, although I've added a little bit about how it protects us, causing stars to twinkle, not a great problem. Stars to appear fainter near the horizon, that can be a wee bit of a problem. Ruining dark adaptation. So the way to avoid that is if you're looking at a star chart and you're looking to see where meteors are moving, just use a red torch or a red filter. You can get night mode on sort of tablets and iPads and things like this as well. So various apps, you can switch them into night vision mode, and you'll see this lovely red sort of glow. The eye isn't sensitive at night, the rods anyway, to red light, so it doesn't affect them. All the other colours it does. Good. Right. So that is that. What I need to do now is to see whether we've any questions in the chat.